Hey, this is a quick demo of the work I've been doing with the Redis Sidekiq experiments. The goal of this is to get to a base load where we can see roughly production level performance out of Redis in the smallest environment we possibly can, and then experiment with the various mitigations that we've got proposed and planned and reasoned out to see which ones are going to actually have an impact, to confirm that we're going to have an impact and see what the scale of the impact is. The full details are on Scalability issue 956. I recommend you go and look at that. If you have any questions, I'm going to skim over a lot of it here. Very, very quickly, let me share my screen. I want to share this one here. Okay. Right. Ignoring the other things, I have three instances. I have a Redis node, a client node, and a Prometheus node. The Redis binaries, I totally kiddoed this. It is simply binaries copied from production. Compiling was a pain, it wasn't worth it, and it's actually slightly nicer to be really sure I've got the same binaries I've got from production or staging. So I've got 5.0.9, that's the older one, 6.0.10 straight up, and 6.0.10 patched, which is with our BR pop fix that Igor and Matt worked on together. The configurations have been very, basically from production, very lightly modified. Just where necessary, setting directories and setting up simple passwords. I don't have to care about that particularly much. Cool. So that's the client node. We select with a little wee shell script. 6, so it's either 5, 6, or 6p, 6 patch, and then run, which selects the configuration file and just runs. So that's done, out of the way, no problems. On the client, this is a little bit more complicated. So we have created the worker classes. So you don't run this here, you run this in the GitLab code base from the top level. It looks at all the queues, and for each queue generates a simple class that sleeps. So it's not exactly a one-to-one mapping. In the code base, it's weird in terms of the classes and namespaces and which queues they get put into. What matters is that we've got a class per queue that we've got, and that they do something. The sleep is a random duration, and if we look at application worker, basically we've grab these numbers out of Kibana at various percentiles, 10% intervals, and P95 and P99. And we randomly choose one of those. So what this means is that the jobs will be flowing through at a good rate that mimics production to some degree. I mean, we are talking 10% up. The bottom 10% will take only 0.02 of a second. We've got to be able to throw a lot of jobs through. But this gives us a reasonable layout, a reasonable shape for those jobs, for how long they actually take. We ignore the last 1% above P99, because it gets up to like 1500. Some of these jobs take 10-15 minutes to run. It's not interesting in the scale of what we're trying to do. We're looking at the high throughput stuff. A single Sidekiq worker just sitting there doing nothing for 30 minutes, as far as Redis is concerned, doing nothing. Not relevant. So that's the workers that are ready to run. We run them with a little wee Sidekiq thing, so it's literally Sidekiq itself configured. We just require all the files, configure it, put it in Redis. We must use a semi-reliable fetch. This is interesting. We'll be able to do this again when we get past this to the single queue per shard. We'll be able to test with the fully reliable fetcher in this environment and see what it does, because that uses a completely different Redis command. Redis commands are pop or push instead of br pop. So we set that up, and that's the simplest thing. Sorry, 1 second. And right, and then we can run it with this. So we literally, I've also copied in basically most of GitLab embedded from production. So this means we can run the Sidekiq binary with that Sidekiq Larvae, which configures things and a shard configuration. And we've got some logging. So we can run multiple of these to simulate a full fleet of Sidekiq workers. So the configurations look like this. So this is just the concurrency and the queue lists, which we are basically the same as production. Got the list of the queues with Sidekiq cluster driver, and we'd thank goodness for that. Whoever wrote that, love you. It's worth noting, just in case you're not fully familiar, that Catch-all has two fleets of workers, VMs and K8s, Kubernetes. The VMs are running the ones that we still think might or do need NFS. Kubernetes ones are the ones that have validated explicitly do not anymore require NFS. They are two discrete sets of workers from the Catch-all shard, the ones with no resource boundaries. So that runs Sidekiq. So with this run multiple Sidekicks, I can run a whole bunch of them in background. And so with all of those running, and it looks a little like I will run them sort of like that. So I will run them, I'll run the Catch-all VM shard, I'll run 56 of them. I grabbed those numbers literally from our current production number of running workers across VMs and Kubernetes and pods and processes under Sidekiq cluster and all that sort of stuff. So if we're trying to get the same number of worker threads from Sidekiq talking to Redis. And then, so with Redis running and the workers running, we then generate jobs. Very, very simply. Again, load all the workers, connect to Redis. For each type, effectively shard, we schedule one class. I think this is okay in terms of what we are trying to test here. Every time I think about it, it bounces back and forth in my head. I think Redis doesn't matter for performance particularly much whether we are putting work into one queue or work into 20 queues. I think just because it's single threaded and it's only one data structure, there's no locking to worry about. So I think that's okay. I'm going to have to get a little bit further than that to do some of the other experiments we want to do. So we will see what happens then. But I'll be putting that off because it's not quite the tests we really are interested in. Very brief, basically, I just stuff a whole pile in. These numbers here are the production worker counts. I was originally thinking that I'd be able to stuff work in faster than the workers could pull it out, but that's not true. Turns out it's actually quite a bit of overhead, more than we would think in getting the work into Redis in the first place. So I do that. I've stuck with that. I haven't gone back and re-edited it because I can generate production-like load. And then we just schedule the work in here. So I actually do it twice, and that's still barely keeping up. So in practice, we actually find we need to run this generator twice. So it's really cramming work in there as fast as it can, 2 or 3 times to get load up to base load. What we also have, so that's the base load. We also have, for example, 1 queue per shard from the 1 queue per shard experiment. The only difference is this here. So instead of simply performing on the class, it sets the queue explicitly. So it overrides all of the other work that's going on to select the queue and just uses that name there. And so then we have slightly different config files for Sidekiq. Elasticsearch. There, where it just listens on 1 queue. So to see it in action, Redis is running up here. We want to start the workers. So I will start the workers. We will do the full original load. So we run that there. I'm tailing all the logs over here. This takes a minute or so to start up. I'll just run top here. So this is the client. This has got 16 CPUs. The load goes nuts for a bit, as you would expect, but that's fine. Wait for that. Let me find Prometheus. So this is the graph of Redis CPU. So this is just Redis itself. Our Prometheus is scraping like every second. yeah, we'd never do this in production, but I want to see the subtleties of the variations over time because we're working at such fine grain. So at the moment, Ruby is still starting up, doing its thing. I would normally be terrified by that, but it's fine. Now we wait for these logs to start to, there we go, they're all started up. Load goes up, and we will see in here, here we go. This is our base load, gradually rising, let's drop that down. So our base load, this is also with the BR pop timeout set to 5 seconds, which is what we're running in production at the moment. 2 seconds is worse than this. So very good, we get up to about 30%. This might stabilize in another few seconds. Yeah, just rise at the start when everything's connecting. Oops, they must have been catching up a few jobs. Cool. Probably from my previous tests. There we go. So there we go. That's the startup time, and it stabilizes at about 12%. That's consistent with our previous experiments. So this is a full load of clients simply sitting there listening for no work. And we will run the generator. And we will run it twice. So this is really throwing queues in there. Once, rubbish. That's running once. Just showing you how long it takes to schedule all those queues. It's about 3 seconds. It's quite a bit of 3 to 4 seconds. And then we will run 2. And just trust me on that this is a good thing. So you can see all the workers doing their thing. I'll just cancel that for a second. So yeah, 1.374 seconds. Quite a few of those at that. And so on and so forth. 761. Yeah. That's interesting. I'll look at that. So that's busy, those are busy doing things, and we can see what's happened over here. We'll just take 2 minutes. And there we go. So with 2 generators, we can get our Redis up to about, actually you can see where the first one started 1 and then started the second. About 90%, which is actually pretty close to what we're seeing in production right now at our peaks. So there's lots of variations here. This is not entirely accurate, but it is order of magnitude there. And not only order of magnitude, pretty close order of magnitude. So I'm very happy with this because then we run all the other experiments, which you can see all the results of, and we can see what happens to that, like dropping this down from 90% down to 50%, which is awesome. Hope that makes sense. We can get access to this. It's not well set up, but I mean, if I can drop your SSH key on there, hit me up. We can run experiments, and we can do this in the future there, which is awesome. Thanks.